Alright guys, hello and welcome back to the channel again. So we're continuing our discussion on the second part of electromagnetism. Most of it is already done, just a few small concepts are left. One of those which we'll be discussing in this video is the idea of the transformer. So with the transformer, you probably know that you have two sides to the transformer. This is what's called the primary side, this is the secondary side. On the primary side, we apply an alternating voltage, and its working is also asked really often. So we'll also get to that in a minute. So for example, 3-mark questions where you are asked to explain something like this, which is that describe how an alternating voltage at the primary side leads to a voltage or a current at the secondary side. And we'll get to that in a moment. So what is a transformer really? For example, all of you may have seen PMTs, which are pole mounted transformers. And these are just, this is just a device that changes the voltage levels of alternating voltage or alternating current. So if you give it 1 voltage, it can give you another voltage. So for example, if you give it 220 volts, it could probably give you 10 volts or the other way around. So the construction of the transformer is in such a way that you have a primary side as shown here, you have a secondary side, and these are wound around a soft iron core here as shown. So what is the purpose of the soft iron core is because it would get induced because of this, it would have magnetism induced in it because of this current flowing through the primary side. What happens is that this basically channels, focuses the magnetic field lines because of the current or the voltage in this one all the way to here. So that basically reduces energy losses and increases the efficiency of the process. So how does this work? And another similar question which is asked sometimes in MCQs is why can a transformer not work if instead of AC we had a DC supply here? So why would that not work? So the idea is this, that when you have an alternating voltage or current at the primary side, this also gives rise to an alternating field. Because the voltage is alternating, so the field that it produces is also alternating. And in this way, it's kind of similar to the loudspeaker because we talked about this exact same idea there as well. So for example, sometimes the current would be flowing like this, other times it would be flowing in this direction. So by the right hand grip rule, where the north pole is constantly going to be changing. So the field lines are constantly changing. So sometimes the field lines are like this, for example, other times the field lines would be in the other direction. So what that would mean is when the field is changing in the primary, this would also cause a change in the magnetic field across the secondary. Keep in mind that no voltage is applied on this side, right? Voltage would be induced in this side. So the changing field in the primary causes a changing field across the secondary as well. So as the iron core channels, focuses those magnetic field lines across the secondary coil. Or you can also say this, that field lines are cut by the secondary coil. Again, it's the same thing. It's basically Faraday's law of electromagnetic induction. So whether you say there's a rate of change of magnetic flux linkage, which some people find a bit heavy on the tongue to say, or you can say a changing field, or you can say that field lines are cut by the secondary coil, all of these would work. And because of that, there would be EMF induced across the secondary. And sometimes the examiner does ask this, that sometimes the examiner would just ask that how does a voltage on the primary lead to a voltage on the secondary as well. And sometimes it says how does it lead to a current here. So then you also need to say that because that EMF is provided across a closed loop, so an induced current flows. Now, obviously, as we just talked about this, the transformer would not work with DC, and now you know why. because in that case, if it's DC, so there would be no rate of change of a magnetic flux linkage. So because no field lines would be cut by the coil. Okay, so two equations for working with the transformer that you do need to know. So previously we've talked about this idea that the greater the, what do you call it? The greater the turns, the greater would be the induced EMF. We talked about this in the last video when we were talking about the AC generator. And the idea is that it's really proportional. So the idea is that if two quantities are proportional, if I write it like this, then their ratio is the same. So what then ends up happening after some math, the equation that you're supposed to know is this one, which is Vp over Vs is Np over Ns. And this equation basically says that the ratio of the voltage at the primary side to the ratio at the secondary, to the ratio of the voltage at the secondary side is equal to the ratio of the turns at the primary side to the turns at the secondary side. But then we also know that, for example, if you're talking about 100% efficiency, so if power is constant then, so I can also say that since P equals to VI, and I can also talk about I here, the other equation that we get is this, that IP over IS is actually, because power is equal to VI, so you can say that voltage and current are basically inversely proportional, right? So then what happens is that if we talk about voltage to, if we talk about the ratio of voltage of primary to secondary, so here it's also the same because they were directly proportional. But in the case of the current, what would happen is that the current is actually inversely proportional to the turns ratio. So what happens is that the ratio flips. So here, if we're talking about the primary current to the secondary current, it's actually the ratio of the turns of the secondary to the turns of the primary, right? So this is Vp over Vs, this is Ip over Is, but for voltage, it's Np over Ns. So exactly in the same order as the voltage, but for current, it's flipped, right? So this is something that you need to know. And how a transformer works is that by changing the number of turns on the primary and secondary, we can either step up voltages, which means we can increase them, or we can similarly decrease them. And those are the examples that we're going to look at now. So if you have a step-up transformer, that means it's increasing the voltage. So because of this relationship that we looked at, if we want the voltage at the secondary to be greater, then naturally the number of turns on the secondary also have to be more. So here you would say more voltage and similarly turns on the secondary side. And then obviously if you have more voltage and turns on the secondary side, this would mean less current on the secondary side because of the inverse proportion. Now let's have a look at this example. So we're given the number of turns on the primary voltage, primary current, secondary voltage. We have to find the electrical power produced, secondary voltage, secondary current, assuming 100% efficiency. So for the electrical power, this is supposed to be really easy. We know the formula P equals to VI. So the power produced is all of that is transmitted onto the secondary as well. So I know the primary voltage, I know the primary current. So that's just 20 times 10, which is 200 watts. What about the secondary voltage? So for that, I can use the equation in terms of the voltage and turns that we just saw. So I can say Vp over Vs equals Np over Ns. Once you get the hang of it, you'll see that it really doesn't even always have to be like this. You could also flip this, but then you would also have to flip this. So the idea is that whatever is the ratio, whatever is on top for the voltage, be it primary or secondary, also has to be on the top for the turns. So for example, if I need to find Vs here, and this is how I like to do it, is first make the is to first do the algebra and make the variable the subject of the equation. So Vs, for that I would need to cross multiply here and here. So Vs would become Vp Ns over Np. So Vp is the primary voltage, which is 20, and S the number of turns on the secondary, which is 500, and Np is the number of turns on the primary, which is 25. Right, so I just need to work this out now. So 25, that's 25, 4 is 100. So 4 times 5, this is 20. So this is turning out as 400 volts. Let's see if our answers make sense according to the concepts we already know. So for example, what I know is that on the secondary, if the turns are more, so the voltage also has to be more. And that's exactly what is also happening in this case. So yeah, this is exactly what I would expect. For the next part now, there are two possible methods. One of these is related to this idea that if you've already found the power and if you now know the secondary voltage, you can just use the power formula and figure out the secondary current as well, which is just P equals to VI. But just so you guys understand how the equation would look like for the currents, that's why I'm going to use that one. So let's say I write it like this. So IS is what I need to find. IS over IP, but for turns, because it's inversely proportional, that's going to flip. So that would be NP over NS. So I need IS, let's make that the subject. That is NP IP over NS. So I just cross multiplied by this here to get IS as my subject. So NP IP, so 25 into 10 over NS, which is 500. So that turns out to be 0.5 amperes. And you would get the same thing, as you can probably already see, using P equals to VI. So this would be P, this would be V. And by dividing, you would get I as 0.5 amperes back again. What's a step down transformer then? Obviously, with a step down transformer, you need to decrease the voltage from primary to secondary. So you'd also need to decrease the turns. So this time you have less voltage and turns on the secondary side. And obviously this would mean more current on the secondary side. Now we also have a problem that we can solve here related to step down transformers. So as you can see, that here in going from primary to secondary, the number of turns are reducing. So the voltage would also obviously reduce. So first part, again, electrical power produced. So if it's 100% efficiency, the power that's produced at the primary, all of that is transmitted to the secondary side. Obviously, that's not always true, but that's what this example is saying. So power equals VI. So 50 times 7.5. Let's do this. So that turns out to be 375 watts. Primary voltage, so again, Vp over Vs equals Np over Ns. So Vp is then equal to Vs Np over Ns. Vs is 50, Np is 100, Ns is 20. This is 5, and 5 times 50 is 250 volts. Again, this makes sense that the voltage at the primary must be more than the voltage at the secondary because we're stepping down the voltage. Part C, primary current. Just for the sake of diversity, let's try to do this one using P equals to VI. So I already have P, right? So that's 375 equals to 250 times I. Let's solve for I now. So that's 375 divided by 250. This turns out to be 1.5 amperes. And you can also do this as an exercise for yourself where you try to find out the current using the turns ratio method. Again, you would probably get the same answer. Now, what are the use of transformers? Why do we even talk about these? So the idea is that, for example, if we're traveling between cities, we always see that we have like voltage being transmitted over these long distance overhead lines, and that's done at very, very high voltage levels. Why is this the idea? That because if I'm talking about at constant power, if I'm increasing the voltage, then I'm basically decreasing the current. So if I talk about it this way, P equals to VI. So if I've increased the voltage levels of transmission, then I've reduced the current. So this is because at constant power, increasing voltage reduces current. And then if I think about this power formula, which is P equals to I square R, which is why that reducing the current has also led to lower power losses. So this means that there's less loss, so that's increased the efficiency. And there's also another advantage of this is that this also increases the life of cables, because if there's less heat produced, so it would obviously last longer. So it's transmitted at really high voltages. Then again, when we reach the consumer side, that voltage is stepped. Okay, so this is not written. It's stepped down again. So it's stepped down again to the consumer side, and then we use it for our purposes. So this is power produced at some station using whatever method is there. Then that stepped up, transmitted through long distances. On the consumer side, it stepped down, and then we use that power for our purposes. So that's the idea of the transformer. In the next and last video, we'll be looking at how oscilloscopes work. So see you there.